to our video on section 5.7 on complex fractions. So what is a complex fraction? Well, anytime you have a fraction that has a fraction or decimals within it, then it's a complex fraction. It can also be a fraction that has negative exponents in it. So for example, we have a number example of a complex fraction where we have, again, fractions within the fractions, both in the numerator and the denominator. In addition, we want to know that because the negative exponents here are separated by addition, or in this case subtraction, they cannot just move to the other side of the fraction bar. So literally we would have to write this as 1 over x minus 1 over y divided by, or over, 1 over x squared minus 1 over y squared. And so it creates this complex fraction or fraction within a fraction. So we're going to be looking at two methods today for solving all complex fractions. You can choose which method you prefer, and I will not ask you to do a particular method on any kind of assessment. So in the first method, we're going to simplify the numerator and denominator separately, and then we're going to divide. In method 2, we're going to multiply both of the fractions, or the numerator and the denominator, by the LCD of all fractions. So to start, it's easiest to begin with a number example that we see here. So if we were to get a common denominator for just the numerator, which has 3/4 and minus 1/8, we would use 8. So we would have to transform the first fraction by multiplying by 2 over 2, and that would give us 6 over 8 minus 1 over 8. In a similar way, this denominator, the 2, doesn't have a fraction, so we would need to multiply by 12 over 12 to get a common denominator. That would give us 24 over 12 plus 1 over 12. We could now add the fractions in the numerator. 6 minus 1 is 5 over the common denominator of 8. And in the denominator of the complex fraction, 24 plus 1 is 25 over the common denominator of 12. So as a reminder, the fraction bar can be thought of as a division symbol. So we can rewrite this complex fraction as 5/8. Instead of the fraction bar, we can say divided by 25 over 12. And as you may recall, when we have division, we want to remember that dividing is the same thing as multiplying by the reciprocal. So we're going to rewrite that problem as 5/8 times the reciprocal of 25 over 12, which is 12 over 25. Now we are able to do our cross canceling. 5 and 25 both divide by 5, and 8 and 12 both have a common factor of 4, so 8 divided by 4 is 2, and 12 divided by 4 is 3. And so now when we multiply across the numerator and across the denominator, we have our simplified answer, except I made a math error. Other than that, we're good. 2 times 5 is 10, not 5. So looking at the next method, what we're going to do is I'm going to write the question again. And again, that's going to be 3/4 minus 1/8 over 2 plus 1/12. And I'm going to look at the denominators here of 4, 8, and 12. And I'm going to ask myself, what's the LCD of all of those numbers? Well, they share a 4, but then I'm also going to need to make it bigger again than the 12. So I'm going to, because again 8 wouldn't work. I'm not going to be able to convert 8 to a 12. So the LCD is going to be 24. Remember, the LCD is also the LCM, the least common multiple. So what I'm going to do is I'm going to multiply, and I'm going to write this over 1. I don't always, but I want to make sure that you see where this is going. By using the LCD of all of those denominators, I am going to be able to eliminate the fractions that are in both the numerator and the denominator of this complex fraction. So when I multiply 24 times 3/4, what happens is I get 24 over 1 times 3/4 minus 24 over 1 times 1/8. And of course, there's going to be cross-canceling that happens here. So I'm going to end up with 6 times 3, or 18. And here, 24 divided by 8 is 3. So I'm going to have minus 3 in the numerator. And then for my denominator of the complex fraction, again, when I distribute that 24, I'm first distributing to a number, 2 over 1, so that's going to just give me 48. And then I'm distributing the 24 over 1 to the 1/12. And of course, that's going to reduce to just 2. So now what I have is 18 minus 3 over 48 plus 2. That gives me 15 over 50, and now I can reduce because both of them have a common factor of 5. If I divide by 5 for the numerator and the denominator, I get the same answer as 3 over 10, which I got for the first method. Now this second method may look a little bit more complicated, but once you get used to it, it actually has a lot of benefits. So let's look at our first rational expression. So here we have x minus 1 over x divided by 1 minus 1 over x. So if I use method 1, so I'm just going to mark this up here with a 1. When I'm using method 1, I'm simplifying the numerator and then simplifying the denominator. So the first fraction is the common denominator would be x. So I would multiply the first term by x over x, what it's missing. That would get me x squared minus 1 over the common denominator of x. In the second fraction, it's the same denominator, so I would multiply the first term by what it's missing, which is x over x, and that would get me x minus 1 over x. Now recall that the fraction bar is division, so I'm going to rewrite this as x squared minus 1 over x divided by x minus 1 over x. And division can always be rewritten as multiplying by the reciprocal. So we keep the first fraction the same, change the division to multiplication, and then we use the reciprocal. Well, we can see that x squared minus 1 can be factored to x plus 1 times the quantity of x minus 1. So we're using, in this part of the problem, we're using the same methods that we did when we were simplifying with multiplying and dividing rational expressions. So we're looking for common factors. X minus 1 can cancel, and the common factor of x can cancel, and we're left with our answer of x plus 1. Now if we look at method 2, again I'm going to start by just rewriting the problem. And that problem was x minus 1 over x over 1 minus 1 over x. In method 2, we're going to look at the denominators of the complex fractions and see that they would be an x in both. So I'm not going to show the same number of steps that I did in the original example, but I'm going to remind you that I'm distributing, and this is x over 1. I'm distributing that to each of the terms in the complex fraction. So when I distribute the x to the x, nothing cancels because there's no denominator. So I get x squared, x times x. When I distribute to the 1 over x, the x's cancel. I get x over x, which is just minus 1. In the denominator of the complex fraction, when I distribute to the 1, nothing's canceling, so it's just x times 1. But when I distribute to the 1 over x, I get x divided by x, which is just minus 1. So what I did was I cleared the complex fraction by multiplying by the LCD of all of the denominators. Now I can go ahead and factor the numerator. The denominator is already in factored form, and I can see that I have a common factor. We're, of course, going to end with the same answer. If we don't, then that means we made a mistake in one of the problems. Our answer for both of those would be x plus 1. So let's look at one of these examples that has the negative exponents. So here, we're going to first rewrite this problem. 1 over a minus 1 over x divided by 1 over a squared minus 1 over x squared. It's really important that you do that first. So we're going to start with method 1, which means that we're going to combine the terms in the first part of the problem. And the common denominator we would use would be ax. So I'm going to multiply the first term by what it's missing, which is x over x. The second term by what it's missing, which is a over a. Likewise, in the denominator of this complex fraction, the common denominator would be a squared x squared. The first fraction is missing an x squared. The second fraction is missing an a squared. So now what we end up with is x minus a over the common denominator of ax divided by x squared minus a squared over the common denominator of a squared x squared. So again, we're just transforming these fractions to get a common denominator. And now we're going to recall that we can rewrite this as division. So the fraction bar becomes a division symbol. I wrote that denominator wrong, didn't I? My apologies. A squared x squared is what that should be. And so now we're going to rewrite the division as multiplying by the reciprocal. So x minus a over ax, change the division to multiplication. A squared x squared now goes to the top, or the numerator, and then I'm going to factor the x squared minus a squared as I write it down here. Just save us one little step. So I have common factors that I can cancel. And here, the ax and the a squared x squared, this is going to leave me with just an ax here. So what I end up with for my final answer is ax in the numerator and x plus a in the denominator. Let's take a look at method 2 for the same problem. So the first thing, just like I did with method 1, the first thing I'm going to do is rewrite it. And that's going to be 1 over a minus 1 over x divided by 1 over a squared minus 1 over x squared. So in this problem, I'm going to look at the LCD of all of the denominators, and I'm going to use a squared x squared. So I'm going to multiply by a squared x squared in the numerator and in the denominator. And recall that I'm now going to distribute to all 4 of those terms. And what happens when I distribute, I'm going to write this out the long way because this one's a little harder to see maybe. When I distribute here, I get a squared x squared over a minus a squared x squared over x. When I distribute to the denominator of that complex fraction, I get a squared x squared over a squared, and then a squared x squared over x squared. Now I'll do all of my canceling. Here, the a squared over a becomes just an a. So I'm going to just rewrite this as ax squared. And here, the x squared over x becomes x, so I'm going to have a squared x. In the denominator, the a squareds cancel, so I'm left with just x squared. And here the x squared cancels, so I'm just left with minus a squared. So let's go ahead then and rewrite this so it looks a little prettier. We have ax squared minus a squared x in the numerator and x squared minus a squared in the denominator. Now we're going to look to factor. The numerator has a GCF of ax. We're going to take that out, and we're left with x minus a. The denominator is the difference of squares, so we factor to x minus a times the quantity of x plus a. We have a common binomial that we can cancel. So we're left with our same answer, obviously, that we got in the first method. We're going to be left with ax over x plus a. Okay. So I am going to do one more example, and then actually there's two more examples. So let's get to the next example, and I am going to use method 1 for example for the next example, and then method 2 for the final example. So we'll do one of each. So in this first, I'll do method 1 here, and that means that I'm going to find a common denominator for the numerator separately from the denominator. So it looks like I'm going to use x squared. So the first term is missing an x squared. Let's go ahead and rewrite this, otherwise we're going to be squeezing too much in. Okay, so to get to a denominator of x squared, the first term needs to get multiplied by x squared over x squared. The second term just needs to be multiplied by x over x. And the third term doesn't need to be multiplied by anything. In the denominator, the LCD is going to be x. So the first term of 1 is going to need to be multiplied by x over x. But the second term doesn't need to change. So what I end up with in the numerator is x squared plus 3x plus 2 over the common denominator of x squared. In the denominator, I end up with x over x plus 2 over x, which gives me x plus 2 all over the common denominator of x. Now let's rewrite the division, or the fraction bar rather, as multiplying by the reciprocal. So x squared plus 3x plus 2 divided by x squared. Change the fraction bar to division and then use the reciprocal. So now we can rewrite the division as multiplying by the reciprocal, and that's going to give us x squared plus 3x plus 2 over x squared. Change the division to multiplication. The x plus 2 goes to the numerator and the x goes to the denominator. We're now going to go to our methods for simplifying when we're multiplying, which means that we're going to factor then cancel. We're going to factor the x squared plus 3x plus 2 to x plus 2 times the quantity of x plus 1. I'm just going to write the x squared as x times x. That's going to help us a little bit. Let's see. I think I may have written that wrong. X plus 2 over x. I did. When I wrote it here, I wrote it backwards. So let's fix that. We weren't going to have anything that cancels, and I thought, wait, I think something does. So that is a mistake that you don't want to make. So now what I have is x in the numerator and x plus 2 in the denominator. And that's going to allow me to cancel out these common factors. And I am left with x plus 1 over x. Okay, so our last example, we're going to actually use method 2, so you get a little bit of everything. And in method 2, recall that we're going to look at the LCD of all of the fractions. So it looks like it's going to be the same though. So we have a k minus 2 in the denominator of the numerator and a k minus 2 in the denominator of the denominator in the complex fraction. So I'm going to multiply by k minus 2 over k minus 2. Just recall that that is getting distributed, and the point is to cancel out all of our fractions. So nothing cancels when we distribute to the k because there is no denominator. So we get k times the quantity of k minus 2. But when we distribute to 1 over k minus 2, we get k minus 2 over k minus 2, which is just plus 1. When we distribute to the denominator of the complex fractions, the k minus 2 cancels, so we're just left with k squared. But when we distribute to the 1, nothing cancels, so we actually have plus k minus 2. So now what we're going to do is distribute the k in the numerator. And we have a trinomial divided by a trinomial, so we're going to look to see if we can factor to cancel. The perfect square trinomial in the numerator, and the denominator is going to be k plus 2 times the quantity of k minus 1. And we look and we see, hey, we've got a match in the k minus 1. So we're going to cancel out those common factors, and our final answer would be k minus 1 divided by k plus 2. Now, as a side note, if we were to do a question like this and it was in some sort of function form, we would want to remember that the restriction from the domain would be negative 2 and positive 1 based on the domain. And then, therefore, if we did the zeros, we actually wouldn't have any zeros because we've already excluded the 1. So that's kind of an interesting question where the exclusion will give us no zeros. So that concludes this rather long video on complex fractions. We will be working on those questions in class next time.